The channel, scientists have developed a method to work out how quickly a radioactive sample decays. In other words, how quick is radioactivity happening? So in this video, we're going to be looking at that method and how it works. So in this example we're going to use here, this sample contains 25 atoms altogether. There are 16 unstable atoms, and these are represented by the green ones. So we'll label them. These green atoms here are unstable, so they have an unstable nucleus. And the yellow ones, these have a stable nucleus. These are stable. Obviously, over time, the yellow ones are going to undergo radioactive decay. And it's impossible to know and predict exactly when each of these atoms is going to decay. We can never say, we can never find out, oh, that one's going to decay at this exact moment. So it's pointless to even try and watch each individual atom. But what we do know is that over time, they will break down. And over time, this is going to happen. So what we see in the second diagram, as you can see, certain atoms here have decayed. So this one here that I'm labeling, you can see that this has decayed. And what you will notice about the second diagram is that we have gone from, in the first one, having 16 unstable nuclei. So there's 16 unstable nuclei here, to having half that amount, 8 unstable nuclei left in the second situation. So what we've done is we have taken the atoms, the number of unstable nuclei, and we have multiplied it by a half. Okay, so 16 times a half gives you 8 unstable nuclei. So this happens over time in a radioactive sample. And obviously that's going to take a certain amount of time for half of the unstable nuclei to decay. This amount of time is known as one half-life. So in one half-life, the number of unstable nuclei in a sample decreases by half. Okay, so it goes from 16 to 8 in this example here. Now, different substances that are radioactive have different times for this. Okay, so one of them might take 100 days. One element, the isotopes, might take 10,000 years. It doesn't really matter how much time it takes. What's important is to understand that it's the time taken for the radioactive nuclei in the sample to decrease by half. So what if we wait again until the number of unstable nuclei halves again? So here in the third diagram, you can see that we've now gone to 4 unstable nuclei. So the number of an unstable nuclei in this sample has halved again. So we've taken 8 and we've times it by a half. So we say that this amount of time again has passed, and this amount of time we call one half-life. Now, because this is the same sample, so it's got the same isotopes, it's the same element, we can be pretty sure that these two things are the same amount of time. Because it's pretty consistent, it's a pattern within a certain element. Okay, and like we said before, there's no way of predicting exactly when each type of atom is going to decay, or each particular atom is going to decay. There's no point in looking at, okay, let's look at number 3. When is that going to decay, this one here? We don't know that. But what we do know is that after a certain amount of time, half of them will have gone. Half of them will now be turned into yellow ones. They will be turned into stable nuclei. And only half of the original unstable nuclei will remain. We call this amount of time one half-life. So again, if you were to predict, now I don't have it drawn, what would happen in the next half-life? So after one more half-life, we would have 2 unstable nuclei left. And obviously this keeps going till you've got none left. All right, now let's just look at a couple of points over here. What is half-life? The definition is shown in red there. The half-life is the time taken for half of the nuclei in a sample, in a given sample, to decay. Okay, so the time taken, half the nuclei. So again, that's in red. That's the definition. You need to make a note of that in your keyword dictionary. I want us to read this little next point together. Okay, so I'm just reading here. Okay, so you can, I'm going to let you read it yourself there. So I'm going to just give you 20 seconds to read that. Okay, so what is this saying? This is just saying that different substances, different elements have different amounts of time for their half-life. So carbon-14, for example, carbon-14, its half-life is a very long 5,730 years. So that's how long it takes for a sample to decrease by half. Okay, so the rate, the nuclei to decay by half. So if you had 1 million unstable nuclei in a sample, after this many years, 5,730, that would now be 500,000 unstable nuclei, and the rest were turned into stable nuclei. Okay, while the half-life of lithium-8 is much smaller, obviously here, it's less than 1 second, 0.838 seconds. So really, really quick. So that one turns stable really quick because every second, half of the nuclei are gone. So if you've got 1 million nuclei, every second that'll be half a million, 500,000, 250,000, 0.125 million. And again, I'm not even sure what comes next. So it is found that half-life though is reasonably consistent for each isotope, meaning that 16 nuclei of carbon-14 would halve to 8 nuclei after, and sorry, there's a typo here, this should be 5,730, the same as it was up here. So 16 nuclei of carbon-14 would halve to 8 nuclei of carbon-14 after exactly that many years, and precisely 5,007 years later, it would have halved again to 4 unstable nuclei. Again, that's just recap on what we did in the experiment, in the diagram, in the example, sorry. Okay, so to make sure that we've understood this, what I want you to do is we're going to do these questions here in question 164. Okay, so again, I'm just going to go through the first one with you to make sure you understand how it works. The half-life of an isotope is 10 minutes. Okay, thinking about what that means. Okay, so that means that every 10 minutes, the number of radioactive nuclei in a sample will decrease by half. It has 20 million radioactive nuclei. Okay, and then it's saying which of the following is true. So you've got 3 options, A, B, and C, and we have to just say which one is true. Okay, so the amount of time they're giving us is 10 minutes, 10 minutes, 10 minutes. Okay, and it's saying after 10 minutes, there are 5 million nuclei. After 10 minutes, there are 10 million nuclei, and these should all be radioactive nuclei. Sorry, radioactive nuclei. That should be in all of them sentences. Apologies about that. After 10 minutes, there are 10 million nuclei, or after 10 minutes, there are 20 million radioactive nuclei. All right, so which one makes sense? Okay, well, the half-life is 10 minutes. So this time here, this 10 minutes, this is 1 half-life. Well, after 1 half-life, how many radioactive nuclei will be left? Well, all you got to do is take how many there was in the beginning, 20 million, and you got to times it by half. Okay, so 20 million by half, hopefully that's very simple, it's 10 million. So which one is correct? B is correct. All right, so you go ahead and finish those other 2 now, okay? And I'll see you in the next one.